kids.
All right. Hey, I wanted to give you guys a quick, probably 10-minute review of the circular gravity unit, just so it makes sense to you. All right. So anyway, we started the unit with, if you guys remember, you did a whole bunch of different demos. The purpose of those demos were to, number one, show you that if you are moving in a circle, okay, you are accelerating. Okay, why are you accelerating? Because you're always changing your direction. And remember, the direction of the acceleration was centripetal. It always points towards the center. Number two of those different demos, if you guys remember, you had the penny on the hanger, the penny spinning around, the marble going around the paper plate. All of those were trying to show you that, you know what, an object is trying to move straight, okay, and an object will continue to move straight due to inertia. If you remember the paper plate puzzler, it looked like this. So I had that marble going around, and at this point, it went off tangent to the circle. So an object is trying to move straight due to inertia, and it will continue moving straight unless some outside force prevents it from moving straight. And in the case of like the penny on the hanger, it was the hanger. In the case of this, it was the paper plate or whatever. Okay, so remember, moving in a circle, accelerating, wants to move straight due to inertia. The acceleration points towards the center. Okay, that was some of the basics there. Couple other basic terms was period. Okay, and again, just think as far as think obvious stuff. Okay, physicists, we pick words that are obvious. This is currently, I don't know what time it currently is for you guys. For me, it is currently fourth period, so that's a cycle of time. So it's the fourth period. So that when we're talking about period, to find it, it's the time divided by the number of revolutions, so the number of cycles. So like, hey, what time is fourth period? You wouldn't say, well, it's the fourth time. No, you would say, it's 10:30 or whatever it is. Okay, frequency is the next thing. Okay, just so you guys are aware, period is abbreviated capital T. Frequency is how frequent something happens, which is why it's the number of revolutions divided by the time. Okay, lowercase f. Obviously, if you look at these two, you'll see that they are related by that. That equation is on your formula sheet. These equations are not, because the College Board and us, we expect you to understand definitions. That's definitions. If something is moving in a circle at a constant speed, again, it is accelerating, but if it's moving in a circle at a constant speed, I can find how fast it's moving by using this equation, V equals d over t. Oh, V equals d over t. Oh, that means that the d around a circle is the circumference, 2 pi r. That equation actually is on your formula sheet, believe it or not. And then the time that it takes to go around this once is the period. So 2 pi r divided by that. What other basic stuff? I think that was the basics. Oh, and then this one was v squared divided by r. If you guys remember, we did a lab where you guys looked at centripetal force versus speed, and you got a square relationship. Well, that means that centripetal force versus this would be a linear relationship, and the slope of this would have been equal to, I don't know if you remember from the stopper lab, but it was equal to m divided by r. So that means my equation is Fc equals mv squared over r, where that was that slope that we're talking about. Okay, but a lot of times we did Fc equals mv squared over r. All right. So that was kind of the beginning stuff of this unit. We talked about some of the basics, and hey, you need to understand some of the basic terms with that. Then we also played, if you guys remember, we played Crack the Whip. We had the people lined up like this, and they were rotating around. Remember, this person was moving the fastest. This person really wasn't moving. This person was then moving the next slowest, and so on. Why? Because they all had the same period. This guy had a bigger, so if you think about the equation, For the guy on the outside, R is bigger, this is the same, so that's bigger. You know, the guy on the inside, R is 0, so that's 0. Okay? But yeah, we talked about that. And then we did all of our problems for this unit. I really want to emphasize to you guys, this class is not about memorization, understand. So with all our different problems, we had some of the problems where it's like this. Hey, you're going in a vertical loop. You know, maybe it's a roller coaster going around a loop to loop. If it's a roller coaster going around a loop to loop, you have free body diagram at the top, free body diagram at the bottom. At the top you would have Fn and Fg, and then at the bottom you would have Fn and Fg. Now here's where you shouldn't be memorizing stuff. It should be about, hey, I understand, it makes sense to me. You know, remember, if you're moving in a circle, you have to be accelerating towards the middle. So, hey, well, which way is towards the middle? Well, this way is towards the middle. So what does your equation have to be? It has to be Fn minus Fg equals mv squared over r. Where at the top, which way is towards the middle of the circle? Well, that way is towards the middle of the circle. So I get Fn plus Fg equals mv squared over r. And there is questions like, hey, where is it most likely to break? Well, if you solve for Fn, you would get, or down here you would get, oh look, it's going to break, it's more likely it's going to break at the bottom. And you guys saw that, the swing fail video. But anyway, again, it's not about memorizing, like every problem is potentially different. So, you know, and here's what I mean by that, guys. Like, if I have a car going over a hill, okay, now it's a different Fn, it's a different Fg. In this case, you know, if you draw your free body diagram, it would be, hey, I have Fg, I have Fn, and it would be, oh, wait a second, if it's going over the hill, down is towards the middle of my circle. So then it would have to be Fg minus Fn equals Fa or Fc. You know, if it was, hey, you're moving in a circle and you just barely make it through, well, that means at the top, the only force acting if it barely makes it through is Fg. So then you'd say Fg equals mv squared over r and whatever. So like, but again, the key is it's not a memorized game. It's understand, draw your picture, write your equation, figure stuff out. We also did horizontal circle stuff. Remember, if you have a car, okay, and this car is going to go around a corner, what is causing the car to move in a circle? Well, friction is. That if there's no friction, your car is going to move straight. So like if you were to, this would be a top view, but if you were to look at a back view of the car, so this is looking at the car from behind, I would have Fn, I would have Fg, I would have Ff pointing towards the center, okay? If you write your equation, Fn minus Fg equals 0, and then you would have Ff equals mv squared over r, and it is the point turning to the right, okay? And you can plug stuff in and solve. So horizontal circle. We had some horizontal circles where it was like, you know, if you remember the flying pig, you know, that lab where it's like, hey, I got a pig, it's going around in a circle, I have tension pulling on it this way, well, I still have gravity acting on it, and really that's the only two forces acting on it. So what forces are causing that pig to move in a circle? Not Ft. Ft parallel is causing it to move in a circle, okay? Where Fg perpendicular would equal Fg, so it'd be like, hey, I'm gonna write my equations, you know, and my other equation would be Ft parallel equals MAC or mv squared over r, and again, plug stuff in and solve, okay? But it shouldn't be a memorized game. It's, hey, understand it, apply it, you know. By all means, I would encourage you guys to practice those. But even there, don't just memorize, because, you know, if you have some other weird question that comes up, like, I don't know, it could be, you know, a gravitron custom where you get pressed up against the wall. You know, in that case, what's causing you to move in a circle? Well, the wall. The normal force is, you know. Then you'd have friction holding you up. You'd have gravity pulling you down if you're stuck to the wall in the gravitron. You know, we did like the little penny lab, but just, again, don't memorize, understand it, try it out, you know, and it should make sense. All right. that was the beginning part of the unit. The second part of the unit was we're talking about universal law of gravity, which was Fg was equal to Gmm over r squared. Again, I typically write it big M, little m, because most of the time you're going to have a big M and a little m. Like, for example, the force of gravity from the Earth right now is acting on me with a force of about 180 pounds. Well, what are the two m's there? M from the Earth, M from me, okay? We talked about how this is related to Fg equals mg. Well, that means then G is equal to that, okay, where G was equal to Gm over r squared. We had questions where problems like this, where it's like, hey, if the mass of the Earth tripled, so like if the mass of the Earth was tripled and the radius of the Earth was doubled, you know, what would happen to your force of gravity, or what would happen to G? You know, those type of questions. And this is just a proportional reasoning thing, and however you guys solve it, be able to do it. The way I do it is I say, hey, if you look at my equation, m is proportional to Fg, so far I'm times 3 as big. If you look at my equation, r is an inverse square relationship to Fg, so if I take the inverse of this, I get 1/2 squared, I get 1/4, so it's going to be times 1/4. So that means my G or Fg, because it's really the same as far as that stuff goes, it'd be 3/4 as big. So if the Earth was 3 times as massive, 2 times the radius, I would weigh 3/4 as much as what I weigh right now. All right, so that, hopefully that makes sense. The whole reason we talked about this unit, or we put gravity in this unit, is, hey, if I have the Earth and I have some random spaceship orbiting the Earth, for some reason it looks like a TIE fighter, if it goes around in a circle, all right, so now I do the steps. The only force acting on it is Fg. So then I would say, hey, you know what? Fg equals Fc. But then I'd have to be careful because it's Fg is Gmm over r squared equals mv squared over r. Now hopefully it makes sense if I make big and small m's. One of my r's goes away. And then you could solve for all kinds of cool stuff like, hey, how fast is that spaceship moving at a certain distance away? You know, whatever it is. That a couple things you do have to be careful with, though, guys, with these problems. A lot of times is the wording, and this is why you want to, you know, like actually draw a picture and write it out. Don't be that kid that screws it up because you didn't draw a picture. That a lot of times it'll be worded something like this. The spaceship is at an altitude of 2 of the Earth's radius. Well, that means this would be 2r of the Earth. Okay? Well, then my r here is not 2 because I would have to add that r. Okay, so just be careful with the wording with that. But again, I would strongly recommend you guys draw a picture. It'll make more sense. You'll do better. I've never had a kid go, gosh, I got that wrong because I drew a picture. Okay, I've always had kids that go, geez, I wish I would have drawn a picture. Don't be that kid that wishes he would have. All right, everybody okay there? And then the other part for this unit was we talked about Kepler's laws. Kepler's laws were, hey, I got the sun. Okay, first law is, hey, things going in orbit or an ellipse. Sorry, I can't see that very well. Let me make it so you can see it better. Okay, first law is things go around in an ellipse. The orbits are actually ellipses. Remember, a circle is a special ellipse. Okay, second law was this. Okay, equal area and equal time, so that this area equals this area. What is the second law actually saying? It's actually saying that, you know what, as you get closer to the sun, it speeds up. Why does it speed up? Well, there's a couple different reasons. You could do it in terms of, here's my v, there's my force of gravity, okay, pointing towards the sun. There's a component of it that points this way. That causes it to change direction. And then there's a component that points the same way. That causes it to speed up. So, hey, this is causing it to change direction. This is causing it to speed up. So as it moves towards the sun, it speeds up. Okay. You could also do it in terms of energy. Okay, going from here towards the sun. that it loses potential energy. Remember the whole negative thing with UG in space, but it does lose potential energy, so that therefore it gains kinetic energy, speeds up. That was the second law. And then the third law was that t squared, r cubed thing, whatever. But how do you do that? Here's what I would recommend to you, is you do this, guys. You say, hey, you know what? I know that if I have the sun, okay, and I have the earth or whatever, the only force acting on it is the force of gravity, okay? And again, if we simplify this and we say the earth is moving in a circle, and the earth really is pretty much moving in a circle, you could say, all right, I have Fg equals Fc. Well, this is Gm over r squared. This is mv squared over r. Do a little bit of math, cancel some stuff out. So I end up with a v squared. Well, what is v? If it's moving in a circle, v is 2 pi r divided by t. So therefore, v squared would be 4 pi squared r squared over t squared. And then now if you cross multiply, all of a sudden it's like, oh, it's going to be r cubed over t squared. So I get gm over 4 pi squared equals r cubed over t squared. And then, hey, the reason this was a constant is because this stands for the mass of what you're orbiting around, in this case the sun, and then the rest of the stuff is going to be a constant. And then this is kind of cool because you can use things like, hey, if I want to know what is the period of, I don't know, some random planet. Okay, remember we said if this was 1 AU, and we know for the Earth, so this would be 1 AU, and we know for the Earth it's 1 year, so that this thing, which is a constant, is 1. So that if you wanted to do some random object that its R was 4.5 AU, then here's how you would solve it. You would say, all right, my new R is 4.5. I'm going to cube that over t squared equals 1. And let me grab a calculator real fast. Okay, and so I go 4.5 raised to the third, 4.5 raised to the third, and then I take the square root of that, and that object would, the period for that object would be 9.54 years, Earth years. Okay, so anyway, there was Unit 3, and I don't know how long that took, but hopefully not too long. Bye, kids!